People have used solar energy for many thousands of years. First as a form of heating, eventually they harnessed it to in the form of solar cookers and for other applications. In 1830, the British astronomer John Herschel used a solar collector to cook food during his expedition to Africa. Of course, now the solar energy is used in all forms and especially for production of electricity. Our sun is a blob of gas made of hydrogen and helium. It has a diameter of 1.4 million kilometers and has a distance of 150 million kilometers from the Earth. The estimated temperature and pressure is about 15 to 25 million kelvins and 300 billion atmosphere. On the surface, it emits radiation and it appears as a black body radiation at 5800 Kelvin. Sun's radiation comes in all forms and all wavelengths. About 48% of the radiation of the sun is in the visible and another 46% is infrared. Every second, sun loses about 4.3 billion kilograms of mass while producing enormous amount of energy. This is a spectrum of the solar radiation. The graph on the top shows that solar radiation peaks on the visible range and then tapers off toward the infrared and ultraviolet. The graph at the bottom right is radiation from the Earth. As it appears, the intensity of radiation is about 6 orders of magnitude smaller, 10 to the power of 17 compared to 10 to the power of 23, and the peak is shifting at 10 to 12 microns. So the Earth is radiating in the infrared, the sun, most of the energy is in the visible. The graph in the middle is of a black object or another metal, in this case gold, that at the melting temperature of the gold, and again you can see that very little of that is in the visible, but most of it is in the infrared. The intensity of solar radiation is the amount of the radiation falling on a plate which is normal to the solar radiation. The intensity is about 1400 watts per square meter outside the Earth's atmosphere and about 1000 watts per meter square reaching the Earth's surface. This if it were directly overhead. The sun is, however, rarely directly overhead and its position changes throughout the day, limiting the solar power average over a 24-hour period to only 1/4 of the solar constant, or about 340 watt per meter square. To determine the amount of the radiation reaching us or any location in the sun at a particular time, we have to determine what is the position of the sun relative to us and what is the position of us relative to some fixed reference of points on the Earth. The position of the sun is determined by two angles, altitude or theta and azimuth, which is phi. If you raise your hand toward the sun, the angle that your hand makes relative to the horizontal plane, is called altitude. During the sunrise and sunset, the altitude is 0. At the high noon, the altitude is maximum. The second angle is the azimuth. It is the angle which is measured relative to the north-south direction. It is zeros at the north and 180 degrees at the south direction. The complement of altitude sometimes is used instead of the altitude, and that's called zenith. That's the angle that the sun is making toward the normal to where we're standing. Of course, once you know the altitude, you know the zenith, so these are not two independent angles. The position, our position on the Earth, can be measured with two angles also. These two angles are the latitude and longitude. Latitude is the angle that our position makes relative to the equator. If we draw a line between where we are standing, in this case Wausau, and the center, this line makes an angle which is equal to longitude with the plane of equator. So for the Los Angeles or Long Beach where we are standing, the angle is about 33 degrees. On the equator, the latitude is 0. In the North Pole and South Pole, the latitude is plus 90 and or minus 90 degrees. The second angle is the longitude. That's the angle that determines our position with respect to an imaginary circle passing through the city of Greenwich in England. So if you are in Greenwich, the longitude is 0. As you go toward the east, the longitude becomes positive. Going west, the longitude becomes negative. Basically, this is the great circle that determines the west from the east. Since the Earth is rotating 24 hours a day, every 24 hours, therefore for every hour, the Earth rotates by 15 degrees. In Long Beach, the longitude is about 133 degrees. And so, in order to the Earth to rotate to where position of Greenwich is right now, we have to wait somewhere between 8 and 9 hours. Every hour is 15 degrees. That's the time difference that we would expect between LA and Greenwich. By the way, these are the two angles that's also determined by your GPS in your car. Once you know these two angles, you can identify your position on the Earth uniquely. The Earth is rotating about the Sun in an elliptic fashion. The ellipticity is not very high, so the ellipse is very much looks like a circle. The difference between the long axis and short axis is only 6 million kilometers. The distance of the Sun, the closest distance of the Sun to the Earth, is on January 3rd equal to 147 million kilometers, and the largest distance is on July 4th, which is 152 million kilometers. Some of you might be wondering why the Sun is farther away from the Earth during the summer, or on the other hand, why the summers are hotter than the winter, although our distance from the Sun is larger. Well, the answer is the tilt of the Earth. The Earth has a tilt of 23.5 degrees relative to the plane of motion around the Sun. In the summer, the Earth is tilting toward the Sun. So if you are in the northern hemisphere and you're tilting toward the Sun, the southern hemisphere is tilting away from the Sun. That's why the seasons are reversed. When it is summer here, it will be winter in the southern hemisphere. 6 months later, the Earth is tilting away from the Sun. So if it was summer, now it is winter. 4 times in the year are of particular interest. The winter solstice is around December 21st. That's when the days are shortest. We have the longest nights. The summer solstice, we have the shortest nights and the longest days. On 2 other days, which are autumn and vernal equinox, days and nights are exactly 12 hours. So let's say in the winter solstice on December 21st, where we are standing, the night could be 14 hours, the day is 10 hours. After winter solstice, the days are getting longer and longer until the first day of spring. On March 21st, which is called vernal equinox, days and nights become of equal lengths. Days continue to get longer and longer until summer solstice around June 21st, and the day could be 14 hours and the day could be 10 hours. At this point, the day has the longest lengths. After this day, the days are getting shorter and shorter until on September 21st, first day of autumn or fall, day and night are 12 hours again. The days are continued to get smaller and smaller until the shortest on winter solstice, and the process repeats again. This is the position of the Earth related to the Sun on the summer solstice and on spring and fall equinoxes. So where do we have most intensity of radiation? The most favorable places lie between 15 and 35 degrees north, covering the land masses of many developing countries of Northern Africa and Southern Asia. They receive on average 3,000 hours of mostly direct sunshine and limited cloud coverage. The moderately favored belt is about 0 to 15 degrees north, or called an equatorial belt. It has a high atmospheric humidity and cloudiness that tend to increase the proportion of the scattered radiation, reducing annual direct sunlight to about 2500 hours. The intensity is almost uniform throughout the year, since the seasonal variations are slight. Moving further north, there is a greater percentage of the cloud cover, which sharply reduces the solar radiation intensity. This is a map of solar insolation for the United States. As the diagram shows, the best region for the solar technology is in California, Nevada, Arizona, which you see the reddish color, darker color. As you move toward the east and north, then the annual radiation intensity drops. The sun does not always rise and set from the same place. In the northern hemisphere, sun appears, if you're facing south, to rise behind you, goes in a high angle, reaches maximum point at the time which we call it solar noon, and then drop back and set behind us again. That is going from the northeast and set at the northwest. The angle altitude is high. In the winter, however, we have a smaller angle, and the sun appears to rise in front of us from the east and sets in front of us in the west. So during the winter, we have a lower angle, so we could have theoretically, we can have sunlight for a longer period of time. This is for the northern hemisphere. For the southern hemisphere, everything is reversed. Our winter is their summer and vice versa.